All right, so let's take a look at our first problem for which we are asked to develop the shear force function and the moment function. And I think it would be a waste of your time right now if I were to calculate the support reactions. Instead, I'll just tell you that for this problem here, we really have support reactions RAY that was equal to 10.4 kilonewton in this case. And RBY is really equal to 9.6 kilonewton. So, of course, we usually would have an RAX in this case, which is equal to 0. So I'm going to eliminate that. And now I can go ahead and develop my functions. If you are struggling with calculating the support reactions, please go back in some of the previous lectures. We definitely discussed that at length. That is something, as you can see here right now, that you need to be quickly able to do, because that is just the starting point for these problems. So let's go ahead now and actually develop the functions. And to do that, what I will do is I will first break down my system into two domains. So I clearly have two domains here because I have a domain that is consistent from here to over there, and that is domain 1. And then here I have domain 2 because the functions will be different within that domain. And so now I have to really create two cuts. I have to create a cut for this system here and then maybe a cut for this system. Let's go ahead and do that. So I'm going to use the space down here where I'm originally supposed to calculate the internal forces, but I will just create my cut. So let's cross this out and say that we're going to do a cut for 0 is less than x is less or equal than 8 meters. And the way I can draw that cut is very similar to what we have seen before. So I just have a beam with a length of x. In fact, let's say that this here is x. And I have, of course, a support reaction on the left. And that support reaction was equal to 10.4. And I have an evenly distributed force with 2 kilonewton per meter that acts throughout this entire domain. So this is my evenly distributed force, 2 kilonewton per meter. And of course, I need to include my cut now. So I'm cutting the system right here. Therefore, I bring in my moment, my shear force, and my normal force. And this time they are m of x, v of x, and technically n of x, but let's forget that. That is 0 anyways. So let's go ahead and calculate our moments and shear force. And of course, I'm going to start with my shear force. So the sum of the forces in y is equal to 0, upwards positive. 0 is equal to minus positive defined v of x, minus, or let's start with the 10, so plus 10.4 kilonewton, minus 2 kilonewton per meter, multiplied by x meters. And therefore now I have my shear force function for this domain. So v of x is really equal to minus 2x plus 10.4 kilonewton. But the kilonewton, of course, applies to this entire function. So now I have developed the function for the shear force for my first domain. Let's now go ahead and calculate the moment. So I do that in a very similar fashion. The sum of the moments about point x is equal to 0, counterclockwise positive, and 0 is equal to positive defined moment of x minus 10.4 4 kilonewton multiplied by x meter. And now I want to focus on the 2 kilonewton per meter, which rotates about this point counterclockwise. Therefore, that is positive. So plus 2 kilonewton per meter multiplied by x meters. But that is only the resultant force. So I now need to multiply that by its lever arm, which again, the lever arm rotates about this point. So it's half x in this case. So multiplied by x over 2, also in meters. And now I can rearrange it. I can find that my moment function of x is really equal to minus 2 divided by 2, which is really 1, right? So minus x squared plus 10.4x. And of course, we are not surprised about that result, which happens to be in kilonewton meter, by the way, because we knew before that the moment is really the integral of the shear force. And so you can validate your results. You can take this function here and validate that this really is the integration, or vice versa. You can also take the derivative and arrive here. But I have told you this before, and you have used it in your last homework. Now you can verify it. And so I believe now we are ready. Wrap up domain 1, which was acting from x equals to 0 to x equals to 8 meters. And next, what I want to do is look at domain number 2 so that we can define the function for this region as well. Let's actually do that on the very same page so that I can compare them to each other at the end. And let's just say that now we're doing a cut for domain 8 is less than x and less than equal 10 meters. And so I will now redraw my cut. So I have, of course, a constant and a distributed force acting on the system now. And my support reaction, which was 10.4. And I have my distributed force and my concentrated force as well. So I have this force here, which that was 4 kilonewton, and here I had 2 kilonewton per meter. So 2 kilonewton per meter. Let me now cut the system right here, and let me of course explain that we have a function that goes in this direction with x, and I have to bring in my internal forces. I have the moment and the shear force to worry about, m of x and v of x. And now you have to be careful because your x starts at 0 right here, right? So what I will do now is I will express two lengths now. So I will have to express this length, where this here, of course, is 8 meter. And this here is really x minus 8 meter, right? So please understand that I can now describe everything from here to there in terms of x. So I need this value to start effectively, not from 0 here, but I can think of this as from 0 here. So let's develop the functions for that. And let's go ahead and create the shear force function by the sum of the forces in the y direction being equal to 0. And 0 is equal to minus v of x, which of course is positive defined. And I have a positive 10.4 kilonewton. And I have a negative 2 kilonewton per meter multiplied by 8 meters. So it's actually a constant number, which is not a surprise really. Likewise, I have the negative 4 kilonewton, right? So I have minus 4 kilonewton here. And to no surprise, my shear force function now is not much of a function. It's actually a constant, but we would still write it as V of x is really equal to all of these calculated together, which really is equal to negative 9.6. So it's equal to minus 9.6, and that is kilonewton. And that is something that I could actually have known without running any numbers or without developing this function. Why? Because we know that it has to be constant here because there's no force acting on it. And we know that 9.6 has to bring it back to 0. So therefore, minus 9.6 is the only answer that could have been acceptable here. Let's do the very same thing for the moment, which that becomes a little bit more interesting. So for the moment, I say that the sum of the moment about point x is equal to 0. And 0 is equal to positive defined m of x minus 10.4 kilonewton multiplied by x meters. And in this case, I'm really using x because I want to start from 0 here. So for this, I use the x. But now for this one here, I would use x minus 10, for example. But first, let's do the 2 kilonewton per meter. So now I have to include the 2 kilonewton per meter, which rotates counterclockwise. Therefore, that is positive. So plus 2 kilonewton per meter multiplied by 8 meters. It's already a constant, right? So that is the entire sum of it. And now I need to be careful because that force is really acting at the center, right? So it's acting right there. That means that I need another distance, which is really the distance from here to there. And that distance is really equal to x minus 4, right? So this is x minus 4 meters. So I can use that now and multiply this here by x minus 4, and that is in meters. And that concludes the distributed force. Now I need to calculate the 4 kilonewton times its distance, and that also rotates about this point. So it rotates counterclockwise, which also makes it positive. So plus 4 kilonewton multiplied by x minus 8 meters. And now I can rearrange my equation, and what I would find is that I end up with an m of x that is equal to plus 19.2 minus 9.6 times x minus 8, and the whole thing in kilonewton meter. And of course, this is a result, so therefore I double underline it. And if you now wonder why I did this without doing a lot of calculation and really solving the entire equation above here, of course, I could have calculated all of this out, and I probably would end up with something written in a different way, but that would result as a very similar answer, is because I can verify that I have a moment that is 0 here, and I need a slope that is equivalent to 9.6, and that's where the 9.6x comes in. And so if I start at 0 here, I really need to go over 2 meters, so 9.6 times 2, which is really 19.2. And notice that x minus 8 is really 0 for 8 meters. So this expression here would turn out to be 0 right here, and then at 9 meters it would be 1, right? So I have 9 minus 8, which then would be 1, and here at 10 meters it would be 2. So that's why I actually have a slope of 9.6, and that then with times 2 results in 19.9 2, which makes the whole equation 0 at this location. Now, a better way of doing that is actually by plugging in 8 for x here, because my moment needs to be continuous at this location because I don't have a concentrated moment here. So I can just plug in 8 for x and solve this equation. And if you were to do this, just an example, so you have m of 8, then you would find that you have minus 8 squared plus 10.4 times 8 would really give you plus 19.2 kilonewton meters. And so you can really use this equation here in terms of x to find the moment at any point from 0 to 8 for domain 1 essentially. And what I choose is to find it at the end of the domain by plugging in 8 to find 19.2 to verify that my moment function in the second domain starts at that point. This is not always possible, but in this case it is possible. And of course, I also must have a slope of 9.6 here that has to go down because I have a positive moment because the beam is smiling, that then has to go back to 0. You will see that when I draw the moment diagram. But before we draw the moment diagram and the shear force diagram, let's look at another thing where we can actually use these equations for here and here. That is that we need to analyze where our moment is maximum. I highly doubt that 19.2 is the maximum moment. In fact, I know that it's not the maximum moment. Why? Because the moment is maximum where the shear force goes through 0. And if I, for example, plug in 8 here for x, then I have minus 16 plus 10.4. And that is effectively minus 5.6. And here I have minus 9.6. So that means here we are already at 8 meters passing through 0, or we already passed 0. So that means I have to set this equation equal to 0 to find out at which distance v is equal to 0 so that I can calculate the maximum moment there. So another thing that I would do is I would find where is v equal to 0. So at which location is that the case? And the way I can do that is, of course, setting the equation minus 2x plus 10.4 equal to 0. And that's a very simple case in this case, because all I have to do is take 10.4 and divide it by 2, which then gives me 5.2, and that is 5.2 meters. So what I know now is that from 0 to 5.2 meters, the shear force is positive, and at 5.2, the shear force is actually 0. So this is where v is equal to 0, and therefore that's also where m is equal to max. So I need to know this for my upcoming diagrams, and I need to indicate at what location my maximum moment exists, and I of course need to calculate that. So I actually need to plug the 5.2 back into this equation to calculate my maximum moment. Let's do that actually next. And so that is the last thing that I want to do here on this page. So now I can calculate that m max is equal to minus 5.2 squared plus 10.4 multiplied by 5.2, which really is equal to plus 27.04 kilonewton meter. And that is a significant value that I certainly need to include in my following diagram. So now I really have all my values complete that I need to professionally draw my shear force diagram for domain 1 and domain 2, and my bending moment diagram for domain 1 and domain 2. I can include all significant values because I really have calculated the most important ones here already. But if I didn't do that, I can always plug any value for x into these equations. In fact, you can verify these equations, for example, by plugging in 0 here for X. So if you plug in 0 for the shear force, what you will find is that you have this term turning to 0 and then plus 10.4, which makes sense, right? Because that's our support reaction here. Likewise, if I plug in 0 here, then I have 0 plus 0, which is the moment, and that should be the case as well. And you can verify that further depending on your situations. But that now concludes all the calculations that we need to have here. Let's move on to the next page and graph our diagrams. All right, let's go ahead and draw our diagrams. And as always, I first bring down my domains. We didn't call this domains before, but now you understand that these are actually the domains that we describe by the different limitations. And in this case, I'm just gonna call the normal force the graph on the bottom. So this here would be the normal force in kilonewton in this case. And that was, of course, equal to 0 everywhere. So I'm just gonna simplify my life like this. And now let's zoom in and draw the diagrams. And let's start with the shear force diagram here on the top. So this is the shear force in kilonewton. And I remember that on the left side, I had a value of 10.4. So here I had plus 10.4. And then you can plug in values now if you want to, but remember that we actually went through 0 at 5.4 meters, I believe, if memory serves correct. So I just pretend that's something like that. And then we had a value of minus 5.4 here. And of course, we needed a jump of 4 right here, that we then ended up at minus 9.4, which then led to a constant description in domain 2 with negative 9.4. And of course, we need to go back to 0 here, so that here we have minus 9.4. This is our negative region, this is our positive region. And we need to indicate our slope really, and that's why we calculated the function. So we could say, for example, or one way of describing this would be that from here to here, we're really looking at a function that we determined to be minus 2x plus 10.4. And the other function here was really given with a constant. So that's already actually included in the diagram, but this was a constant of minus 9.4. And this should all make perfect sense now, because there's really nothing new in the diagram that you see right now except the equation here. But you can verify this from before. You have a support reaction of 10.4 here that then is reduced by 2 kilonewton for every meter you go to the right. And if you go to the right over 8 meters with 2 kilonewtons per meter, starting from 10.4, then of course you end up at minus 5.4, which is now verified by this equation. And so we can really use these equations as a fail-safe method to really find the value everywhere along X. We also use this equation to find out where our shear force function is really equal to 0. So remember that we did that for this distance here, and we found this to be 5.2 meters, which I will now use to draw my moment diagram, which is up next, because I know that at that location, the moment must be a maximum. And also, I can already tell that the moment function must be x squared, because the shear force function is in terms of x, and we have to integrate or step up one. And I have a positive slope on the left to this line and a negative slope to the right of that line. So that means that my belly has to go positive up here and then negative down, or like it has to decrease here. And then here I have a constant slope. So let's go ahead and calculate that or draw that. So I draw the moment in kilonewton meters here. And of course, I start with my easy points, or the easiest information that I can get access to. So I know that my moment must be 0 at that location. I know it must be 0 at that location. And then I believe we calculated it to be here 19.2 if I'm not mistaken. So that was plus 19.2. And we had a maximum value of 27. So plus 27.04 if I'm not mistaken. And I remember that I had a function that was linearly sloped right here. And then I have a parabolic function that now has to have the belly in this direction. And I try my best to describe this like so. And now I have my complete bending diagram defined. I, of course, need to include my functions in just a second. So let's indicate that I have these two domains here. One is acting from 0 to 8 and one from 8 to 10. And I calculated the first function to be actually quadratic. And the second one was linear, as you can already see. But let's include the actual functions here. The first function was minus x squared plus 10.4x. And in the second domain, we really calculated that the m of x is equal to plus 19.2 minus 9.6 multiplied by x minus 8. So these are my m of x functions that I have to include with that graph. I have now described fully what's going on from the 0 to 10 meters for the shear force, and for the moment I included all the significant values and I also included the functions. So therefore we now completed and concluded this problem. We are ready to use this concept for any of the upcoming homework problems, but let's take a look at another example for which I want to give you some hints as well. Let's move on to the next page. So now the problem becomes a little bit more interesting because we have a non-evenly distributed force here that sits on the left side of the beam, and we have an evenly distributed force that sits on the right side, and we have to develop the internal force function, the shear and the moment for the entire system, and we calculate the significant values. You can already tell from the shape of these forces and the load case what dimensions or what type of functions we are actually looking at here. For the shear force, we would expect a quadratic function, and for the moment, a cubic function from 0 to 6, whereas from 6 to 8, we would expect a linear function for the shear force and a quadratic function for the moment. So I don't really have to derive this in great lengths. I just want to give you the final answer so you can check what's going on. And to do that, I first want to give you the support reactions. We have one at A and one at B. And of course, it's a walk in the park for you how to calculate these now. But I want to, of course, give you some time savings here by telling you that this is 20 kilonewton on the left side and the other one is 130 kilonewton. So you can use those now to develop your functions. I will now give you the answers on the next page so that you can verify your efforts. All right, so on this page we have to develop our internal force diagrams and list our functions. As always, I start with bringing down my different domains. So let's go ahead and do that for the first domain, which would be from A to B, and then from B to the very end of the beam is where I would have my second domain. And my plan is to put the normal force down here, which happens to be in kilonewton in this case. And of course we know it's 0 and 0, so I need to indicate that, and then I can go ahead and include my shear force and my bending diagram. Let's start with the shear force on the top, V in kilonewton. And I will now include the values that I know, and I will develop this without really calculating the functions. But of course, your job is to verify my functions or my values through your functions. But I know that I have to start at 0 here, and that I have to have a jump which is equivalent to the support reaction, which is equal to plus 20. So I need to have a value of plus 20 here. The next easier thing that I know is that I have to go back to 0 to this location, and that my force is pushing down. So if I'm coming from the left, I have to go down back to 0. So I really can draw a sloped line here, which has a slope of 30. 30 times 2 is 60. So therefore I have plus 60 right here. And then I'm jumping down by the force that the support reaction provides, which is 130. Therefore I go down to minus 70 here. And now I need to have a quadratic equation that really brings the value from here with a relatively small slope, with a larger slope and larger slope and larger and larger and larger slope, back to the minus 70 right there. So now I can draw my entire shear force function along that line. And I know that this is the positive region. I know that this is the negative region and the positive region. So let me shade this. And you can now find the equation to really verify this and to plug in the values for x equal to 6 and x equals to 8 meters here. And then one thing you definitely need the equation for, and that's something I don't give you so that I can really entice you to do this calculation yourself, is to set the shear force function equal to 0 so you can find where V is equal to 0. What is this in meters? That's the big question here. What I can do so that you can verify your results is I can tell you that at this location you have a specific moment. So let's now go ahead and calculate or determine the moment diagram, which is given in kilonewton meters. And now I'm doing this on the fly. You, of course, will verify this through your equations, but I start with my easy points and I use this as a teaching opportunity to let you in on my thinking. So I know that my moment must be 0 right there. I know that also my moment must be 0 here. And I know that I have a maximum somewhere here. I know that that maximum must be positive for multiple reasons. Number one, I can see it here in the slope, but also this beam is smiling here, which is opposite to what's going on here on the right side. Here the beam is frowning, right? So I actually have a negative moment there, and the moment must be parabolic. So it must be quadratic or parabolic, doesn't really matter. And that it has a value of 30 times 2 times 1. So that is actually equal to minus 60. So on this side here, I have minus 60 kilonewton meter. And let's just pretend that's right down here. And again, I have a very high slope, and then the slope gets less and less and less and less until the slope reaches 0. So what that means is I start out with a high slope, I have a little bit less slope, I have less slope, and I have a slope of 0. So my moment diagram in this region must look like this. And now I know that I have a maximum somewhere here. So I have to go through 0, which is of course indicated by the slope, right? So I have a high slope, a little bit less, a little bit less, a little bit less, a little bit less. That is positive. And then I have negative, negative, which gets negative more and more and more. So what that means is I have a high slope that then gets less and less until it hits 0 here. So that looks like this. And then I have to go down here with that very same logic. And so here I have a positive region, here I have a negative region. And now I already calculated the maximum value for you, which I keep that a mystery how I did that so fast. But I will tell you that that maximum moment is plus 37.5 kilonewton meter. And now I have all my significant values described, and I can consider that problem solved. And I say it again, please don't shortcut your knowledge. Please go ahead and develop the function that describes this graph and that describes this part of the graph, as well as the moment function for both domains, so that then you can plug in the proper values. So for example, if you plug into this equation for this domain 0, you need to find a value of 20. If you plug in 6, you need to find a value of -70. And if you plug in 6 for this domain, you need to find +60. If you plug in 8, you need to find 0. Likewise, for the moment, at 0, you need to find 0. At x equals to 6, you need to find -60. And then for the second domain, you need to start with the -60 and end up at 0 for x equals to 8. And then please go ahead and set this equation equal to 0 to find this distance. Plug that into your moment equation so that you can find 37.5 kilonewton meter. And once you've done that, I think you are ready to do your homework. So let's take a look at the following pages and see what problems are waiting for you.